Welcome to the lecture on advanced machine learning. In this topic, we will talk about Bayesian optimization. Bayesian optimization is a class of machine learning optimization method focused on solving problem like maximum over x in A over for f of x, where x is in Rd, typically dimension is less than equal to 20. Typically, A is a region where you want to optimize the or maximize the objective function. It's typically taken as a hyperrectangle, and if is very expensive to evaluate. For example, if is a deep neural network model with L many layers and Q many nodes in each layer. So L could be 2, 3, 4, Q could be another again 2, 3, 4, 5. So my X is L and Q, and F is root mean square error in the validation dataset, or accuracy in the validation dataset. So typical nature of F is very expensive to evaluate. Each evaluation may take lot of time, so, and that might cost you a substantial amount of time as well as monetary cost if you are using cloud computing. If lacks spatial structure like concavity or linearity, most of the time we do not know how the surface of the accuracy functions or the root mean square error or the f will behave. We don't know whether it's a concave function or convex function. We have no idea about this function. When we evaluate f, we observe on f of x and no first and second order derivative are available. So a gradient descent type algorithms are not possible for this kind of optimization problem. So even actually f is a black box function. So f is a black box function, almost like a black box function we don't understand. So if you take f as the accuracy or the root mean square error of a deep learning neural network, so eventually f for us is almost like a black box function where some x for certain hyperparameters we get certain level of accuracy, but we have no visibility about what is the how it looks like. I mean, mathematically we cannot write it down. So goal is find a global rather than a local optima of the f. So Bayesian optimization or BayesOpt is designed for black box derivative free global optimization. Consists of two main components. In the first component, what it does, a Bayesian statistical model for modeling the objective function of f. So because we do not know how f look like, we can evaluate f at certain point of x, certain value of x. For certain value of x we can evaluate f of x, but we have no understanding of how the mathematical function looks like, how the model looks like, and we don't even naturally we cannot calculate the first derivative, second derivative, or the kth derivative. So what people try to do instead of, and we just cannot create a grid over the x and calculate f on each of the grid. Because if the dimension of x is only 1 or 2, then probably we will be able to do it, but if it is like 3, 4, or 5, then we will be almost impossible for us to manage it computationally, however big computational server we may have. So what people try to do, we try to model function f. So we first evaluate the uh, model at different combinations of the hyperparameters, and then we try to model the f, and we try to predict that for a particular choice of hyperparameter, what will be the root mean square error or the accuracy for that model. And we try to find that for which choice from the model we try to predict where we can get the optimal function, and around that area we would like to draw our sample. So that is pretty much the idea. Then second thing is develop a acquisition function for deciding where to sample next. So that is the main two objective that Bayesian optimization actually works on. Here I'm providing a sort of a pseudo code of Bayesian optimization. So first what you do, you place a Gaussian process prior model on F. So here is an interesting phenomenon that I have noticed, that almost more than 90-95% of the paper on Bayesian optimization actually uses Gaussian process prior to model F. But there is no hard and fast rule that you have to use Gaussian process prior to model F. One can ask me that, hey, can I use a spline method, or can I use some other statistical models to model F? Perhaps you can. I mean, there is no harm you doing it, but interestingly, I found this particular niche area completely flooded with Gaussian process prior model. So we are not deviating from the typical methodology. So we will focus on using Gaussian process prior model. The algorithm starts with n equal to n0 points. So there are n0 hyperparameters, and you evaluate f of x1, f of x2, f of xn0. So for suppose you start with 15 or 20 choices of hyperparameters, and in all those hyperparameters you fit the model, the deep network model, and you evaluate the accuracy in the validation data set, and that accuracy is your f of x1. Then you choose another set of hyperparameters, that is your x2, and for that hyperparameter you run the deep network model, you fit the deep net, and once you fit the deep network model you evaluate it on the validation dataset and compute the accuracy, and that accuracy is your f of x2. In this way you do it for certain number of observations, say in 0 is your 15 or 20. Then what you do is you update the posterior distribution of f. So now you treat this x1, x2, xn and f of x1, x2, f of xn 0 and develop a posterior, assume a Gaussian process prior model on f and update the posterior distribution of f given f of x1, f of x2, f of xn 0. Now once you update the posterior probability distribution on f, then second what you do is xn be a maximizer on the acquisition function alpha. So basically acquisition function alpha x is computed using a, so from the posterior distribution you typically construct a acquisition function, and from the acquisition function will give you the function. Now you try to find where the acquisition function alpha x is optimal, and that xn is your next point where you must evaluate the f of x n plus 1 xn, and then what you do, you just increase the n equal to n plus 1 and you go back to the next loop, next iteration. So in that way it's a Bayesian optimization is a sequential method, sequential design optimization method, and you keep it for, you budget it for capital N, say maybe 50 iteration or 100 iteration, and after at 50 iteration you stop and you return the solution, the point evaluated with the largest f of x. So this is how typical pseudocode of a Bayesian optimization looks like, and we will talk about the how this acquisition function look people behave actually uses. There are many different methods in the acquisition function, but what I have taken, I'm going to discuss a very simple method of just drawing a simple random function from the posterior distribution and treat that as an alpha acquisition function. Would just work pretty reasonably well, and I will show you a demo that it actually works reasonably well. So the first step is modeling the objective function with GP regression or Gaussian process regression. So consider the following: y equal to f of x plus epsilon. We don't have any idea about how the f of x behaves, and we can represent the f of x as sum over phi j of x times beta j, and we can write it as a phi of beta. Now where phi is called basis system of fx, where phi jx is completely known, you know everything about the phi j of x, and problem is basically then how you estimate the beta. So this is, again, we are trying to make it into a simple linear model kind of problem. Now what is phi j? Phi j could be your Fourier choices like Fourier functions, or Gaussian Fourier basis like sine omega x, cos omega x, sine 2 omega is cos 2 omega x, where omega is completely known. So if you know the omega, then this entire phi basis is Fourier basis is completely known. Similarly, 1 e to the power minus lambda 1 x minus c1 square, e to the power minus lambda 2 x minus c2 square. These are all known as Gaussian bases, and if lambda 1 c1, lambda 2 c2, these are all known to us, then we know that this Gaussian basis is completely known to us. So we are always assuming this phi is completely known to us, and our main objective is to understand or estimate the or learn the beta from the data. So we are trying to make this nonlinear model, nonlinear relationship between x and y as a or hyperparameter and the accuracy using some linear model, kind of we are trying to put it into a linear model framework, a regression kind of framework, and we are trying to fit this using uses some statistical models like GP regression kind of use things. Now, how the Bayesian methods works. So we start with y equal to f of x plus epsilon, and we're assuming epsilon is follow normal 0 sigma square I. So which means y follow a normal distribution f of x sigma square I. We have written f of x phi of beta summation k equal to 1 to up to k phi k x beta k. Up to this we have written. So if you go back actually here, that is what we have written: j equal to 1 to k capital K phi j x beta j. That is our phi of beta. So we can write it up to this. Then what we have done, we have added a new component which runs from k plus 1 to infinity phi k x beta k, where this part, the sum of this part is less than epsilon. So what we are trying to say that this even if this part is, we have added this additional component, total contribution of this additional component is less than epsilon. Epsilon is our choice, so we keep it very close to 0. So but the advantage is writing in this way. Now f of x can be written as a infinite sum of phi x beta. So this is a kind of sum of infinite functions, infinitely many functions, where we are assuming that after k many components, it is not contributing anything to the value of f. Now still beta are unknown. One way of thinking is, if betas are all 0, then they're all pretty much have no no, this is almost zero, this is all zero. Another way of thinking is this maybe is not exactly zero but very close to zero, so overall this thing is very small, less than epsilon. So that is, so it is not contributing anything to the f of x. Now beta are known as unknown and we want to estimate. Let's just, in Bayesian method, parameters are always considered as a random variable. So here we considered, if you consider betas are uncorrelated random variable and phi kx are completely known deterministic real valued functions, then there is a theorem, very old theorem, Kosambi, Karhunen and Loew theorem, that says that f of x is a random realization from stochastic process. So this function f of x is just a random realization from a random function process. Because beta is a completely random function, so phi of beta must be a random. Hence, if phi of beta is random, so f of x is also random. So that is the starting point of Bayesian thinking. Now what we are saying that if f of x is a stochastic process or f of x is a random realization of a stochastic from a stochastic process, and if we assume this beta is following normal 0 sigma square I, then we can say f of x phi of beta follows a Gaussian process, and since we are studying it under the Bayesian structure, so we call it Gaussian. Fx is known as Gaussian process prior. So prior on beta is basically normal 0 sigma square, so this is the kernel of the standard normal distributions, we can say. And f of beta, f is that induce a prior on f, because f is phi of beta. Phi is completely known. So since beta is Gaussian, so the prior induced on the f is will also be a Gaussian, and that will look like this. And it will be a multivariate Gaussian distribution effectively. Now prior, mean and covariance of f of x are given as f of x, phi of x, expected value of beta is phi of beta 0, and covariance of f of x is expected value of fx transpose. So after some algebraic manipulation, you can write it as some function of x and x transpose. So you can write f of x as invariant normal phi of x beta 0 k of x transpose and epsilon follow normal 0 sigma square I. So the y of x follow invariant normal phi x beta 0 comma, this is the mean function, and the covariance function is k of x transpose plus sigma square I. So if beta 0 equal to 0, if you take, because remember that if you just go back, if we are saying beta follow normal 0 sigma square, standard normal basically, then my expected value of fx at a prior level is 0. I'm just keeping it as a 0, and f of x is then following normal 0 k of x transpose, and epsilon follow normal 0 sigma square I. So y of x is then follow invariant normal and invariant Gaussian distribution with mean as 0 and covariance function as k of x transpose plus sigma square I. Now estimated value of y for a given x star. So now x star is a new value for which I want to estimate the expected value of y, or at f of x star, or we can say that if mu of x is 0 or phi of x beta 0, then you can write it as if expected value of f of x star given the data x and y. You can write it as k of x star comma x, k of xx plus sigma square I inverse times y. Now this is a matrix of order n. Now time complexity of matrix inversion is order of n cube. So this, if you have too many samples, then this estimation could be a little bit cumbersome. But but for the for Bayesian optimization, we don't see that is typically a problem, because what happens is, because we cannot evaluate if at a many places, evaluation of if is very costly. So we start with a very few samples to begin with, maybe 15, 20, 25, 30 samples, not more than that. If that is the samples that you are working with, then it will work very fast. It will not be a problem. But and then you have to increase the number of samples sequentially, if you have to keep increasing the samples. But if you budget it for very large, say if you want to go up to 1000 iteration or 5000 iteration or 10,000 iteration, remember that as you increase the iteration, your matrix order will keep increasing. If you want to go up to 10,000 iteration, at the 10,000th iteration or the last iteration, you have to invert 10,000 by 10,000 matrix. It will take a long time to solve this matrix inversion problem. So you have to be a bit careful in that way. But typically our experience is Bayesian optimization solves the problem way before you go to the 1000 iteration. It within 50 to 100 iteration, it gives you reasonable answer typically. So my data model is YX normal is a YX is coming for an invariant normal with mean 0 and some covariance function plus sigma square I. So we have now a static parameter alpha, rho and sigma square, and alpha rho is correspond to the covariance function. Typically we take a radial basis function, or typically or known as exponential function, and you write down the likelihood function. This is just a basically, if you look at carefully, this is just the likelihood function of the multivariate Gaussian distribution. You write down the negative log likelihood function in that way, and similarly you write down the negative log posterior distribution, and you pass it through a optimization routine and estimate the maximum likelihood estimate or maximum a posteriori estimate, map estimates. So that's how we fit the model, or we try to fit the F. Now I will show experiment with GP regression and how this how good this GP regression is and why it is so popular. We will consider single x and single y. We consider as this simple function y as a function of sine x by x. You can see that by very nature it's a very non-linear behavior. It doesn't have anything to do with the linearity, plus some noise, and noise is coming from normal 0 tau. So what we will do, we will simulate data from this model and we will pretend we don't know the true function. So while we have the x and y's, once we have only x and y's, we will try to fit the GP regression in that data, and then we will compare that against the actual function. So here I have simulated 500 samples from that function, and now all we have this data, this x values and the y values on the y-axis, and these 500 points that I have here. Using GP regression, I estimated this function. Okay, so it looks like this has one big optima or maxima, and it has two local maxima, and also some bump here is also there, but definitely two local optima is there. Next, one left and one in right correspond to the global maxima, and this is the actual red one is the actual true function. So the blue one is the estimated function and the red one is the actual function. So this is with the 500 data points. Okay, so now that is how we estimate a unknown function using Gaussian process regression. As we model the objective function f by f hat using Gaussian process regression, with f we try to predict the performance of the deep network model for a possible choice of hyperparameter x. So using f hat, so if you go back, we will never know the right actual function. We will never, so all we have these some points, and all we have this using GP regression, we try to fit the original function. So these are the hyperparameters. I can say x are my hyperparameters and y may be the RMSE. I don't know, but I'm just throwing a idea to you. And this RMSE, I want to figure out where, for which hyperparameter choice the RMSE is optimum. That is the problem that we are talking about here. And then what we are doing here is, all right, from this is the, we are using GP regression, and from this estimated function we will try to predict that where my possible global optima is there. And looks like here is the global optima, near zero the global optima is there. But we will see how, whether there is a little bit more to it in the Bayes optimization algorithm. So next we model acquisition function which recommend where will be the next point of hyperparameter. So what we do, we can use f hat, the posterior mean from the GP regression, directly as an acquisition function, or one can sample a acquisition function alpha x from the posterior distribution of x. So one can sample alpha x from the posterior distribution of g of the f, and then use that alpha x to find where the maximum point is, where the maximum is occurring. Corresponding there, you simulate, you evaluate your function. So that will be the thing. So here is my, the red dot function is the original function, and here I start with only 15 values. There are 1 2 3 4 5 6 7 8 9 10 11 12 13, around 15 points are there. You can see there are some purple points are there. Now based on these 15 points, this is the first iteration I am doing. Based on this 15 point, I fit the GP regression. Now you can see that this is not a very good fit. Of course it's not a good fit because I have only 15 points, and of course it is doing some kind of overfitting behavior. We can see it's just exactly almost passing it through the observed points. Then what we are doing, we are drawing a random sample from the posterior distribution. We call it acquisition function. So this green function is the random sample from the posterior distribution. Now what you see, that this acquisition function is optimum, is maximum here, this in this local maximum. This value is larger than this value, so it gives me, on the first iteration, the maximum value is -7. The argmax of acquisition function is -7.4, at which it says that you have the global maxima, or the maxima of the function. Now you have to, if the Bayesian optimization was a gradient descent kind of, if you use a gradient descent kind of optimization problem, and once you get into this local maxima, you will never come out of it, you will get stuck there. But the advantage of using Bayesian optimization is you can, after 50 iteration, what we are seeing that it has reached to the global optima near zero. So here it is the global optima. So The red one is the actual true function which we cannot evaluate at all the grid points. So we used around 50 points here now. Now we have sequentially, and then this blue one is the posterior density plot, posterior mean function, and this green one is the acquisition function. So it's not very smooth, it's a little jittery because I have used a noise in there. But if you don't use the noise, then these functions will be much more smooth functions. But by 50th iteration, we reach to the global optima. So Bayesian optimization is a one very strong tool that one can use to learn the hyperparameters for the deep learning neural networks and come up with the optimal choice of the architecture for the deep network. For any kind of deep network, maybe it is a convolution neural network, or maybe it is a LSTM, maybe it's a RNN, whatever neural network. In fact, any kind of Bayesian, any hyperparameter learning problem, you can use Bayesian optimization and come up with the most optimal function, most optimal hyperparameter at which you should run your model. Thank you very much. See you next week.